Alright, so what we do today is not going to be any different than anything we've done this entire year, actually. We've done Pythagorean theorem, we've done the converse of the Pythagorean theorem. However, what is going to look a little different is how we apply these problems. We're going to do more story problems where you have to create a picture using the Pythagorean theorem rather than giving the picture to use the Pythagorean theorem. So, just to review the Pythagorean theorem, in a right triangle, the square of the length of the hypotenuse is equal to the sum of the squares of the lengths of the legs. The converse would then be switching the hypothesis and conclusion. So if we know that c squared equals a squared plus b squared, then triangle ABC is a right triangle. So we can draw in a right angle there. Now, I'm going to talk through these as if I was just doing these problems on my own. Realize that there are often multiple ways to do the problems, and the way I do it makes the most sense to me, but it may not make the most sense to you. So if there's a different way that you did this, then it's very likely that that is a great method, and it just looks a little different than what I did. So don't discredit what you did necessarily. So I'll read through example 1. A 6-foot board rests under a doorknob, and the base of the board is 5 feet away from the bottom of the door. So I'm looking at this, I'm thinking, okay, I have a doorknob with my door. I have the floor here, and I have a board, and it's 6 feet long, so I'm just going to draw the board. So this is 6 feet from here to here. The base of the door is 5 feet away, so this guy right here. From the bottom of the door, how high above the ground is the doorknob to the nearest tenth of a foot? So this is what I'm trying to find out. What is that length, x? So I can kind of see a right triangle forming. I don't try and draw a right triangle right away. I try and draw a picture, and then I can see that I have this right triangle right here. I'm assuming this is a right triangle because we have the door and the floor, in theory, should be perpendicular. So there are some assumptions here that we haven't been assuming before. So if I do that, I know that x squared is equal to, 6 squared is equal to x squared plus 5 squared, because 6 is my hypotenuse. So I have 36 is equal to x squared plus 25. If I subtract 25, I get 11 is equal to x squared. Take the square root, plus or minus square root of 11. But I know the negative root won't make sense because the height can't be negative. So I know that this height is square root of 11. However, it asks for the height to the nearest tenth of a foot. So if I punch it in my calculator, I get that that is approximately 3.3166 feet. The nearest tenth would be right here. I look back because 1 is less than 5. I'm going to round down to about 3.3 feet. And that is my final answer. For the next problem, a newly planted tree needs to be staked with 3 wires. Each wire is attached to the trunk 3 feet above the ground. So, okay, I have my tree. Bloop, 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 bloop. Got my ground. And it has 3 wires. I'm just going to draw one of them. So here's one wire. It's attached 3 feet above the ground. So this height right here is 3 feet. And yep, already I can kind of see this right triangle forming. And then anchor to the ground 4 feet from the base of the tree. So this guy right here is 4 feet. So here is my right triangle again. I got my hypotenuse is where the wire is. And there you go. All right. It says how much wire is needed for 6 trees. Okay, I'm just going to figure out the length of this wire. So here's my wire. I know that 3 squared plus 4 squared equals the length of the wire squared. 9 plus 16, 25. All right, so W will either be plus or minus 5. Again, it can't be negative, so I know that the length of the wire is 5. So the length of one wire is 5 feet. So one wire equals 5 feet. I need 3 wires for one tree. So one tree will need 3 times that, so 15 feet. But I want 6 trees, so I need 6 times that, 6 times 15. Well, 6 times 10 is 60. 6 times 5 is 30. 60 plus 30 is 90. I believe that's 90 feet, but I don't have a calculator on me right now. Yep, looks like that is 90 feet. So how much wire is needed for 6 trees? 90 feet, exactly. For the next one, it says Carrie made a ramp for her dog to get into her truck. The ramp is 6 feet long and the bed of the truck is 3 feet above the ground. Okay, so we got a truck. We have wheels here. Okay, here's my truck. Little hubcaps. All right, you get the picture. So here's the ground. We're making a ramp to the bed of the truck. The ramp is 6 feet long. So here's my ramp. So this part is 6 feet. The bed of the truck is 3 feet above the ground. So here's the bed. There's 3 feet. The question is, how far from the back of the truck does the ramp touch the ground? So what it's asking for is that. Again, I'm going to draw in this right triangle here. So this right triangle kind of appears as we draw the picture. So I know 6 squared is equal to x squared plus 3 squared. 36 equals x squared plus 9. Was that 27 equals x squared? So when I take the square root, plus or minus square root of 27, if I were to simplify that radical, that would be 3 root 3. But it's asking me to round the answer to the nearest hundredth. So I know I don't need the negative root because this is a length. If I punch this in the calculator, I get that that is approximately 5.20 feet. For the next one, find the area of the isosceles triangle whose base is 24 centimeters and whose legs are, okay, isosceles triangle. I see that. I'm going to draw an isosceles triangle. Now I know an isosceles triangle has at least 2 congruent sides. The base is 24 and the legs are 20 centimeters. Alright, and it wants me to find the area. So that's what I'm trying to find. I know that area is equal to base times height divided by 2. So I need to know the base and the height. Well, I know the base. The base is 24. I need to know the height, so I'm going to draw this in. The height I know is always perpendicular to the base. So I'm just trying to figure out what that is. So now when I'm looking at this, I know that these 2 triangles are congruent. Those angles are congruent. They share a side, angle, angle, side. That means that these 2 segments must be congruent as well. So I can divide that into 2, and I'm going to draw another right triangle just so I can focus on the right triangle since we're using Pythagorean theorem only on right triangles. So that's this guy right here. All right, so now we have, this is 20 centimeters. This guy is 12 centimeters. We don't know our height. So 20 squared is equal to the height squared plus 12 squared. 400 is equal to the height squared plus, what is that, 196 if I'm not mistaken. I'm trying to remember my mental math since I don't have my calculator on me. Oh, all right, calculator, where are you? 12 times 12. Oh my goodness, I can't believe I couldn't remember that. 144. Okay, so I've subtracted that. That's 256 is equal to the height squared. So when I square root it, then I get 16 is my height. So now it's asking me for the area. The area then would be the base times the height divided by 2, which is 192. I can't forget my units on there though. These are centimeters, so the area would be centimeters squared. So 192 square centimeters. There we go. Flip into the back. Next problem. Seth made a small rectangular table for his workroom. Okay, the sides of the table are 36 and 18. If the diagonal of the table measures that, is the table square? Okay, first of all, I want to make sure we understand what does it mean to be square. It's not saying is it a square. It is saying, is it square? Square being an adjective in this case. When you talk about something being square in construction, it just means does it form a right angle. So all this means is right angles. We want it to be rectangular, but it's not rectangular unless we have right angles. All right, so all I know is it looks kind of like this. We have 36 inches, 18 inches, and this guy is 43 inches. So in my head, I'm thinking, well, the only way this is going to be square or have right angles is if this is a right triangle. And it's only a right triangle if 43 squared is equal to 36 squared plus 18 squared. So when I think about that, I get 1,849 equals 1,620. These are not equal, so it's not square. So the sides, if the diagonal, is the table square? No, the table is not square, and that work justifies the answer. Here we use the converse of the Pythagorean theorem. All right, switching over to number 6. Anna has let out 50 meters of kite string when she observes that her kite is directly above Emily. Okay, so I'm going to draw Anna. I'm going to draw Emily. They're hanging out at the park. She's let out 50 meters, and now the kite is above Emily. We'll draw a little tail on the kite. There you go. If Anna's 35 meters from Emily, so 35 meters, how high is the kite to the nearest foot? This is what we want to know. We want to know the height. So again, our right triangle appears in the picture. So we have 35 squared plus height squared equals 50 squared. So if I solve this, I have that height squared is equal to 1275. I take the square root. Height is approximately plus or minus 35.71 meters. It wants to know to the nearest foot. Well, we know it can't be negative, so the height is about 36 meters. Looking over here at number 7, a lifeguard spots a drowning swimmer 40 feet from the beach. So here's a swimmer 40 feet from the beach. That's that part. She runs 90 feet along the beach at that speed. So from here to here, we're doing 15 feet per second. Then jumps in the water and swims straight to the swimmer. So at this point, jumps in, runs straight to the swimmer at 5 feet per second. So it makes sense that we can run faster than we can swim. How long did it take her to reach the swimmer? Well, there's two parts here. It takes me some amount of time to run, and then it takes her some amount of time to swim. So I know that distance is equal to rate times time. Or, in order to find the time, I know that my distance divided by my rate equals my time. So my total time will be the time spent running plus the time spent swimming. Let's use T sub R and T sub S for this. Okay, so the time spent running will be equal to the distance, 50 feet, divided by 15 feet per second. And the time spent swimming will be equal to the distance that I spend swimming divided by the rate that I swim, 5 feet per second. So we need to find this part here. So let's go over here. I know that 30 squared plus 40 squared is equal to that distance squared. So if I solve this, I find out that the distance ends up being 50 feet. So it'll take me 50 feet divided by 5 feet per second. It'll take me 10 seconds to swim, and then 90 divided by 15 gives me 6 seconds spent running. So my total time is 6 plus 10, or 16 seconds. Scooching over here to the next one, number 8. A park is in the shape of a rectangle, 8 miles long, and okay, so we got a park that's a rectangle. A couple things I know about rectangles. We have all right angles. These sides are for sure congruent. These sides are for sure congruent. They could all be congruent, but when it tells us that it's 8 miles by 6 miles, we know that it is a rectangle, but not a square. Okay, how much shorter is your walk if you walk diagonally across the park than along the two sides? Okay, so how much shorter? Well, I'm going to use the distance for, we'll say, the diagonal versus the distance for the sides, S. If I go the sides, that's d sub S. Distance for the diagonal. So distance. If I go along the diagonal, d sub S will be distance if I take the sides. Well, the distance if I take the sides will just be 8 plus 6, or 14 miles. The distance if I take the diagonal, well, there's my right triangle. I know the distance if I take the diagonal squared will be equal to 8 squared plus 6 squared. And if I solve that, I get the distance along the diagonal is 10 miles. So how much shorter is your walk if you walk along the diagonal? Well, 14 miles minus 10 miles, it will be 4 miles shorter. There we go. Another nice one where we got a nice integer there. No decimals or approximating. Whew. All right, last one, number 9. Zoom out for this one, make sure we can see all of it. One leg of a right triangle is 2 more than twice the other leg, and the hypotenuse is 1 more than the longer leg. Okay. We know we're going to find the perimeter. We have a right triangle, so I'm going to draw the right triangle. One leg is 2 more than twice the other leg. So here's the one leg. 2 more than twice that would be 2x plus 2. All right, and then the hypotenuse is 1 more than the longer leg. Well, looking between these two, here's the shorter leg, here's the longer leg. 1 more than that would just be 2x plus 3. And I want to find the perimeter. Well, I have a right triangle. I got to find out what x is. So I can do x squared plus 2x plus 2 squared is equal to the hypotenuse squared. So I have x squared. I know that I need to expand this, and when I do that, that'll be 4x squared plus 8x plus 4 equals, and the right-hand side, 4x squared plus 12x plus 9. Now I see that I have x squares and x's. I have a quadratic equation. I'm going to try and solve this by factoring. So I'm going to get everything onto one side, 0 onto the other. When I do that, I get x squared minus 4x minus 5 equals 0. And fortunately, my leading coefficient is 1, so this becomes an easier one to factor. So as I'm thinking through this, I need 2 things that multiply to be x squared. Well, that's x and x. And I need 2 things that multiply to be negative 5, but then they have to add to be negative 4. Not too bad, negative 5 and a positive 1. When I solve this equation, I get that x is equal to 5 and x equals negative 1. But when I look back to see what x represents, x represents the length of the shortest side. Well, it makes sense that x could be 5. Doesn't make sense that x could be negative 1. So we know that the shortest side is 5. So I'm going to go over here, and just in a different color to help me keep these straight. I know that that means this side is 5. That would make this side, 2 times 5 is 10, plus 2 is 12. And then this side is the one longer than that, 13. So now I know the lengths of the sides. The perimeter of the triangle is the sum of the lengths of the sides. So the perimeter is equal to 5 plus 12 plus 13. Or what is that? 25 plus 5 is 30. So the perimeter, does it give us units? Nope. Perimeter equals 30 units. Now, some of you guys would be able to guess and check that. I'm not very good at guessing and checking, and I could ask you to write a system of equations, or sorry, to write an equation that would allow you to solve that in terms of x, if x is the shortest side. So just make sure you're able to create the equation and then solve that. So, as we look back at the rest of these, there's some vocab that I want to talk about. A Pythagorean triple. Is a set of 3 positive integers, a, b, and c, that satisfy this equation. What that really means is when you look back at these problems, looking at number 9, see how we have 3 numbers that are integers, positive integers, meaning there's not decimals or fractions or anything. Same thing with this guy over here, 30, 40, 50. Or over here, 6, 8, and 10. Or this guy. This guy would not be a Pythagorean triple because we had to approximate it. That was a decimal. Flipping to the front. Another example of a Pythagorean triple, this guy over here. This 3, 4, and 5 because those are all integers. This guy, not a Pythagorean triple because we do not get an integer for one of the sides. Alright, so Pythagorean triples show up a lot, and it's really helpful to know the Pythagorean triples. I'm going to be honest, the only Pythagorean triple I really have memorized is a 3, 4, 5, and then any multiple of that, so 6, 8, 10, and so on. So 3 times anything, and 4, and so on. So that ratio continues. 5, 12, 13, I remember better once we start doing this more in geometry, but every year I have to refresh my memory. In all honesty, on all of these. But if you have these memorized, it could make it easier for you to do some of these problems because it'll make it faster for you. And we know that sometimes if we can do them faster, that's always good. Oh, that's the bell. All right, that's how I did these problems. Good luck.